we're going to be talking about spatial analysis techniques and how to use them to make better decisions. So it's probably going to be a little game of two halves here. We're going to start very gently, talk about what spatial analysis is within ArcGIS. I'm going to start to show some simple techniques, how we can get going with it, and then we're going to gradually ramp it up. Jan's going to take over and show a lot more advanced things. So I should probably introduce myself. My name's Linda Beale. I work on the Geoprocessing Analysis team. This is
Jen Lange. I'm the product manager for spatial analysis.
Okay, so we're going to mainly talk through demonstrations. So we're going to show you how we use it. And as we go along the way, we'll explain why we're using that technique and maybe some tips and tricks as to how we can better use things. You're very welcome to get us to slow down, speed up, stop us for questions. If we're skipping over things, you're very welcome. So we're going to talk through some spatial analysis. We're going to say, I've already said, we're going to start very basic, move to more advanced ones. And the other important factor is we're going to show you ArcGIS. So ArcGIS is everything. That encompasses online, desktop, 10x, Pro, different apps. We're going to try and cover a number of different things to show you that analysis really is everywhere. It's not about what you use, it's about how you use it. So, to carry on with that, ArcGIS, as I say, it's a complete platform. We have online, desktop, server, mobile, developer, solutions, and we have multiple names for each part of that system. If anyone understands ArcGIS perfectly and what they're all called, then please talk to me afterwards because I get lost. But the point of this is really that we have this big ecosystem enabling us to do spatial analysis, and analysis really runs throughout that whole platform. So it's everywhere within it. Analysis tools are embedded in that system. It's part of everything that we do. Within the analysis, there's lots of different parts of it. So there are so many tools. There's about 1,000 now. I think we've given up trying to count how many there are, so we stick to 1,000. And they cover lots of different parts. Some of them are statistical. Some of them are about managing your data. Some of them are about translating your data from one format to another type. We've got 3D, we've got vector, we've got raster, we've got network, geocoding, and obviously then we can also do scripting against those. So we can do scripting in Python, scripting in Model Builder. We can combine the two. We can work in terms of models and workflows, or we can work in terms of just using a single tool to get to a single answer. So it really is a complex set of tools, but ultimately they're pretty easy. They're answering the questions that we want answered. And it's just translating that, what's the question, and where do I find that tool, that really is the key to unlocking the power of spatial analysis within it. So first of all, we're trying to unlock the information out of data. And that's all we're trying to do. We're using data for things that we can't go out and observe ourselves. So either it spans a large area or it spans a large number of time. So we're being able to analyze data to help us answer those questions much more easily. In many cases, we're trying to solve very complex problems. So we know that in the real world, there's so much interrelation between different factors. And by putting these into essentially a sandbox, we can identify those key features that we're trying to look at without all the other additional complexity within the world, so that we can actually pull out and tease out the patterns that we see within that. So we're trying to look at the relationships between places. We're trying to characterize location. And we're trying to see what's important. And, of course, crucially, when we're talking spatially, where? Where is that happening? So we use spatial analysis to solve all sorts of different problems. They could be as simple as finding what's nearby. What's near to me? How far away are certain features? How far away are features that are very similar? What's my neighbor like? What's my neighborhood like? What are features within this area like? So we can add in other data. We can essentially enrich the information that we have to get more information and understand things in context. And context is a really important thing when we're talking about spatial analysis. The concepts of I've got more or less, or something is near and far, is relative to something else. So what's nearby compared to. And working geographically, we have that context. So we can really use that. This is bigger than everything within the state, within the country. So working geographically, we very much get that information. So let's jump straight into doing some demos. Okay, let's close that down. And I'm going to start very slowly. First of all, is anyone here from Alaska? Damn. You're ruining my page. I'm sorry, I'm just going to move it out there, but it's there. Be aware that it's there. I don't want to leave you out. I was so sure no one was going to be here. I was going to go, great, I can zoom in. I'm going to zoom in anyway. So here we have the US. Whoops, don't do that, Linda. Let's go back. The US. Okay. And we have on here some data that are road traffic accidents. So there's a lot of road traffic accidents. And let's just look up. Look, there's even road traffic accidents up in Alaska. So there you go. So we have this very big data set. And really at this number of points that I've got within this data set, I can't make any sense of it. It doesn't tell me anything. We can have a look at the table of contents. We've got a lot of points. So they're all going to be overlapping. I can't see any spatial pattern. At very best, we're seeing more where there are more people, less where there are less people. I mean, that's really all we can pick out. That's not giving me any information. So in order for me to understand that information a little bit more, I'm going to aggregate this up into much larger areas. So I have a good overall picture of what I'm seeing within that. So I'm going to aggregate this to my different states. So I'm going to go into my toolbox here, which is in my catalog, and I'm going to go into analysis, and I'm going to overlay the information into my states. So essentially what I want to do is join my points into states and get that information. Now, because what I want to do is join information from my points to my areas, I'm actually going to do a spatial join, because I'm not changing the geometry of my data for my states. I want my states to say exactly the same geometry. And what I want to do is aggregate the information from my accidents into that. If I actually wanted to change the geometry, then I'm going to want to do an overlay, because the overlay process is actually going to break up the geometry and create a new geometry. So thinking about that, you can understand immediately that the overlay process is going to be a lot slower, because it's going to have to split apart your areas, split apart your lines, whatever it is you're going to do to create a new geometry. So it's going to be a little bit slower. So if all you want to do is add information from one to another, aggregate from one to another area, and keep your geometry of one of those areas, use spatial join, it will be much, much quicker. So I want to join to my state boundaries. So that's my target features. I want to join in my traffic accidents. And you see, the moment I do that, I now have a number of different choices. So the join operation, one-to-one. Do I want to join all of my points, all of my road traffic accidents, into one state? So yes, I do. I want to aggregate that information up. If I didn't want to aggregate the information, I would be doing it the other way around, and I'd be getting I would have all my traffic accidents with the state attached to it each way. But actually what I want to do is make my information smaller. I want to have the state and the number of traffic accidents associated with that. So down here it has all the features that I have in both of those data sets. So these are all the attributes within that. And what I can do here is decide how I want to do that join. I've got multiple number of traffic accidents that I'm joining to one single state. So I have a field in here of population. So if I open that out, you can see that my population is attached to my state boundaries. So I'm only going to have one of those. Nothing is going to change. So I'm going to leave that. But if I come down here and I look at the data set that I'm joining to it, let's find one that makes sense. If I look at time, so this is, we can now see this is in my accidents one. If I right-click on here, we have something called the merge rule. So it's a little bit hidden, but it's a very important thing. Because in here, when it's got multiple traffic accidents, it's attaching to one state. What do you want it to do? How do you want to aggregate that information? Do you want to find the average? Do you want to find the total? Or if you're talking about something like a category, do you want to just use the first value that it gets to? So this is a case that you have to think through this and think which one of these would make sense and what aggregation is it I actually want from that analysis. Now, in some cases, the variables you have attached will make absolutely no sense to do any form of aggregation, in which case, get rid of them. Delete those fields. Because there's nothing worse than having a whole load of attributes attached to your data that suddenly don't have any meaning, and when you use that data set again, or worse, you share it with other people, of course, they don't know that. That information is lost. So you just want to keep the information like the number of fatalities. It makes good sense for me to find the total number of fatalities there. So I can do the sum of that. And all the things like weather, I should be just deleting those. And you can just keep going and it will go up. So there's another little tip. You don't have to scroll down each one of those. You can just hold down the delete and get rid of all of those. So let's do that aggregation. And one last thing here is the match option. So we're doing a spatial analysis here. We're joining from points to areas. How do I want to decide whether that point falls, in my case, within the states? So intersect is absolutely fine. There might be cases where you're doing polygons to polygons and you have to then decide how you want it to overlap, whether you want it if the first centroid is inside of it. So that's the last thing to consider. So let's aggregate those two. You can see it's running down here to make my spatial join. Do I have any questions so far at this point?
Why would you use intersect instead of completely within?
It's actually exactly the same thing if I'm doing points to areas. It doesn't make any difference. But that's a good question. You could do either. It really doesn't matter. Yeah. So that's now giving me my output. It is at state level, because that's what I wanted to do. I wanted to join that information into my states. And now I need to go and change the properties. I'm going to change that to graduated symbols. And I'm going to put in there the join count. So when I do that spatial join, you will always get an output field called join count, which is the frequency. That's the total number, in this case, of points within that area. So now I can see the total number of accidents within my states. And we have much more of an idea, just by looking at that, the overall pattern that we have within our data. So that's one way that you can quickly gain some information on a broad level. But of course, we would expect there to be more accidents where there are more roads. So we want to take that into account. And I can do exactly the same here. So I can do a spatial join. This time I'm going to use the same data set that I just created. I'm going to join in my numbers of my highways. And I want to make sure I get my shape length. And I want to do the total number there. So now I'm finding the total number of lengths of highway by state, and I'm attaching that to the same output that I just created so that I can have both of those attributes within the same field. So that's now giving me this second output. So now I can actually go in and I can use the area to map those results. So I want to take my join count field, which is my total number of accidents. I want to look at the shape length. I think it's that one. And let's do a continuous. So the reason I showed the first one as a proportional symbol and why I'm showing this one as a choropleth. So in this, we're showing the total number of accidents within each one of these areas. I'm not taking area into account. All I'm saying is there's this number of accidents in this area. Now, if you take the example of something like Texas, it's the biggest state on the map. So if I coloured that in, it's going to stand out the most, irrespective of the fact that it may not have the most amount of accidents. So when we're doing a choropleth, which the true wording of that in Latin is value by area, we have to take into account area. So within this map that we've created just now, by taking in the total length of roads, I've taken into account the area, because I'm saying within this physical area there's this number of roads. So it doesn't have to be area per se, it's the thing that takes account of the fact that there's differences between these different states. If I was talking about population and I was doing something like total amount of income, I would be using population as my denominator. So that's the factor that I'd be normalizing it by, because then when I look at the map, I'm truly seeing the pattern of what we expect. So now we can see there's a certain number of accidents in different places, and this is based on the number of roads that we're seeing. Okay. So I'm going to jump to another example here. Still looking at road traffic accidents. But within the last example, what we were seeing was the overall pattern that we were getting within that data set, but we were looking at it within boundaries. So it's pretty easy for me to join from my points to my states. It could have been counties, it could have been your own specific geographies that you're looking at. But what if you just want to see the pattern overall? You don't want to constrain it by boundaries. Some things are not derived by our boundaries. It's not that we reach a point and we're not allowed to go into the next door county. You might very well move into a different county to have things, so you want to see that overall pattern. So in that case, then you want to go to your density tool. So that's down in your Spatial Analyst toolbox, and here we have density. So I'm going to do kernel density, and I haven't turned on my extension. So in order to turn on your extension, you need to go into the Spatial Analyst. No, you don't. You need to go to Customize, Extensions, and turn on your tools. So if you find you go in there and it doesn't work, that's what you need to do. So this will now have it. So now when I open the tool, I now have my density tool. So I can put my accidents in there. Population field. This is saying, is every single one of the points that I have representative of one event? So within this data set, every accident, every road traffic accident there is represented by a single feature. It's a point. In some cases, you might have data where you would have a point, but you would have, let's say, 10 people associated with that. So I might be looking at the number of people in the cars who were involved in the accident. My population field would then be the number of people. So that takes that into account. So sometimes you're going to have no population field. Sometimes you want to take into account from a field that you have within there. Output cell size is automatically calculated, but you can change that. Different resolutions here will provide a more detailed picture. It's not changing the underlying algorithm, it's just how detailed you're actually seeing your results. The important factor in this tool is the search radius. So what that's doing is it's creating a kernel density, and it's aggregating up the information within that kernel, and it's saying how big across an area do you want me to do these aggregations. So you can imagine the bigger the area you use, the smoother your map is going to be. If you use a very small area, you're going to get less aggregation, so you're not going to pick out as much of an overall pattern, but you'll see the local patterns within that. So I'm going to leave it as the default. We did change this a couple of years ago, so now it's a pretty good default setting to find the best distance to use based on the density of the points you have within that data set. So let's run our density tool. So as I say, the advantages of using kernel density is we're not constrained by arbitrary boundaries. So in some cases, that is something you want, in which case you'll be using the spatial join. If it's something you just want to see a broad pattern, then kernel density is the thing that you would want. It's very good in the sense that we're not actually modeling the data. So we're not changing the data in any way. Some of the statistical tools will be finding maybe closer to the answers that you might want, but you are doing some kind of modeling, some kind of algorithms to calculate that data. This is purely calculating the number. So we're not affecting the underlying data within that. So there's a lot of advantage in seeing that pattern without having any impact on the data itself. Gosh, it's taken a long time. Okay. So now we see the overall density. And now, of course, you see now we're seeing much more of the local patterns within that data. So now we can pull out the specific cities where there are accidents in that. So you see we're getting a similar broad pattern as we did when we did the spatial join. We're seeing the overall pattern for the US, but now we're seeing those sort of more localized patterns of where we're seeing a lot more roads and a lot more people involved in that. Kernel density is going to stretch to the full extent of that data. So if you want to clip it out to just your areas, then you can go into the layers, to the properties, to the data frame, and here we have the clip option. So this is the extent that's used. So if I want to specify a specific extent, I want to clip to shape. So what I'm saying is I want to get rid of all this blue here, because really there are no calculations there, that's just out in the sea. So I want to specify that shape. I want to use the outline of my state boundaries. So that's now going to just visually get rid of that information. So now you see that's clipped it to that area. But that's just a visual change. If you actually want to clip out so you have the data for it, then you want to go into the Spatial Analyst toolbox and do an extract by mask. And then that's actually going to physically clip out that data so you have a data set that's just for the US country in this state. So the last feature for me to show you, at the moment we've just been kind of looking at patterns. There's not really a lot we can pull out from that. So what if you want to analyze it a little bit more? You want to actually understand if there are any statistically significant areas of traffic accidents or not. Well, then we can use something called the Hotspot tool. So in this data set, again, I'm still looking at road traffic accidents. And I want to see where there are more or less road traffic accidents in that particular area compared to the overall. So that's what the Hotspot tool is going to do. It's going to look at what the mean for the whole data set I'm looking at. So in this case, what's the average across the whole of the US? And then it's going to pick out those areas that have higher or lower average than that overall country. So the important thing that you're getting from this is it depends. It's back to that concept I was saying about context. So it's reporting exactly what I want to do. I'm studying the whole of the US and I want to make my comparison within that data set. But if you wanted to do your comparison within a single state, then you need to select out that state, because then it's comparing it to the mean of that state rather than the mean of the US. So you will get a very different answer. So that's the importance in spatial analysis of understanding what question it is you're asking. It's not the tools that are giving, that you're using the tools to get the answers. So you have to think very carefully about what question you're asking it. If you ask the tool the wrong question, it's going to give you the wrong answer. So you need to think very carefully about that context of what you want to get within that data. And also when you run the tools, there's a number of different parameters that we have within it that we can fill out. So we're looking at clusters. So the optimized hotspot. So within this, I can input my features. So I'm going to be looking at my road traffic accident as my features, but we also have a number of choices down here as to how we look at that information. So if I want to be just looking at the information by location, it needs to aggregate that data up. So the number of those road traffic accidents. So in this case, it's aggregated it by fishnets. So it's put it into grid squares and counted up the number of incidents, the number of road traffic accidents within each one of those grid squares. Within this data set, I also had data that told me the amount of time that it takes for the accident to be notified, and also how long it took them to get out to that accident. So that's additional information I have at each one of these road traffic accidents. I have that temporal factor of how many minutes it took them to respond to the phone call and how many minutes it took them to get out to that person. So that's given me another set of information that I can analyze. So when I actually select the variable, I don't need to aggregate that information because at each one of these locations I have that additional variable that I'm looking at, the amount of time that it takes. So you see that we have very different answers here. So this is the amount of time it takes from the traffic accident to get to the hospital. You can pick out those areas where it's taken them significantly more time than the average for the country. So these are areas where, if you're looking at the US overall, they're performing poorly. They're taking their road traffic accident victims, it's taking them significantly longer to get to hospital. If you're looking at customer service, so they've notified them of an accident, we see a very different pattern. So this is how long it's taking them to respond to that phone call and get out to the road traffic accident. So all of these things from the same data set that we've looked at have shown us very different answers. It's the same data, I'm asking similar questions, I'm using in some cases exactly the same tool. The importance is it's the question that I'm asking, the context that I'm using in that will help me get the right answer for my analysis. So I think that's pretty much what I've got. Do you want to take over, Jen?
Okay, thank you, Linda. So I like to stand up so that I can see everyone better. Linda mentioned that analysis really across the platform, and the demos that Linda showed is basically on ArcMap. So I tried to show some demos that using ArcGIS Online, as well as ArcGIS Mobile, which is a new desktop application. So my first demo is I have a scenario that consists of many different demos, and this one's using ArcGIS Online. So here's the scenario. What I did was I went to the Department of Education for State of California. I went to their website and downloaded the schools, public schools data. One of the attributes that Department of Education made available is called API score. And in the state of California, the school is measured based on this academic performance index, and it ranges from 300 to 900. So the higher the score, supposedly the better the school's academic performance. So what I would like to do is to analyze the school's data and see if I can identify any spatial distribution and pattern for my school's performance. Okay, let's get started. So here what you're looking at is ArcGIS Online. So I signed in to my ArcGIS Online organization, and I added the school's data that I downloaded from Department of Education. Here I have about more than 7,000 points that shows on this map, and these are all public schools, and I classified them based on the score, API score. So you can see that the darker the color, actually the poorer the school's performance. I think it's like the road accident data that Linda just showed, because there are so many points, it's really hard to identify any patterns because a lot of points overlap on top of each other. So what I can do is, if you remember, Linda did the aggregation. She did the spatial join and aggregate the data based on the state level. So what I want to do is to do something called data binning, meaning that I will create equal area bins, and then I aggregate the points into each of this area. The advantage of using equal area is that I don't have to worry about different area might give people different impressions, a wrong impression. Okay, so what I have here, for the state of California, I have hex bins. Can you see this? Pretty dense. There is resolution of 10 kilometers by 10 kilometers. So, I set the scale dependency so that it's not showing at that scale. So you can see these are the hex bins, and they're in the resolution of 10 kilometer by 10 kilometer. And the idea is that I want to aggregate my school data, which are points. So I want to summarize the schools in each of these bins, and I want to get an average of the school's performance. So one thing I want to point out is that data binning has become more and more popular, and in ArcGIS Online Spatial Analysis, we actually provide different resolutions of hex bins layer as like a common layers so that you can use for analysis. And you can also create these hex bins or fishnets in ArcGIS. So what I can do is I go to my analysis option, go to summarize data, aggregate points. What I want to do is I want to aggregate my California schools into my hex bins, which is 10 kilometers. And I do not want to keep the bins which have no schools fall within it. And I would like to take an average of my API score. And this is actually the same as the merge rule that Linda showed earlier. So it's a similar idea. So I can just go ahead and run this analysis. It will take a few minutes. So I will just show you what I had run before. So this is, let me zoom out a little bit. So this is when after I aggregated my data based on this hex bins for the state level. Now you can clearly pick out some spatial patterns, which neighborhoods have some poor performing schools and which neighborhood has some better performing schools. And it probably helps to show the legend. So if I identify in this bin, I can see that it tells me I have 2 schools fall within this bin. The average of API score is 745. If I go to this one, and I have 1 school in that bin, and the average API is 937. So that seems to be good for the state level. Let me zoom in to Los Angeles County. As you can see, if I zoom in to Los Angeles County, the hex bins that I just used, which is 10 kilometer by 10 kilometer, that looks a little coarse if my analysis scale is this level. So scale does matter when you perform spatial analysis. So if my study area were County of Los Angeles, then I would like to perform the same analysis with a finer resolution of hex bins. So So at this scale, I have 1 kilometer by 1 kilometer hex bins, and then I perform exactly, I repeat the same analysis. Aggregate my schools within LA County into this hex bin. So let me show you the result. Maybe I turn off the... So now you can clearly pick out some spatial pattern after the aggregation of data. So the point here is sometimes spatial analysis is just simple aggregating your data and then it reveals a more spatial pattern. And next, like we can, in ArcGIS Online, we can also create hotspot, co-spot, perform hotspot, co-spot analysis, and that shows you a statistically significant cluster of, in my case, the co-spot would be low API score, and the hotspot would be high API score. So as Linda mentioned, the benefit of doing this analysis is not only you can visually identify the pattern, also it outputs a z-score and a p-value, so you can say how confident you can be that this clustering is not random. Okay? So how many of you are familiar with Los Angeles area? Okay. So those of you probably can have an idea where this is. So I know this high-performing area is actually West LA, Beverly Hills area. So my first intuition is, could this be something related to income? Okay, so in my next analysis, I would like to see the distribution, spatial pattern of income within LA County and to see if that correlates to my school performance data. And unfortunately, I don't have income data. I have the hex bins that does not have income data. What I can do is using what we call geo-enrichment service, and that allows you to acquire additional demographic or lifestyle data to add that to your existing geography. So I have this hex bins. I would like to enrich my data to include income information. So what I can do is I go to analysis, data enrichment, enrich layer. What I would like to enrich is my hex bin 1 kilometer, 1 by 1 kilometer for LA County. And now I can select variables that I would like to add to my existing geography. So the tool is smart enough first to identify where you are. So it shows me that all the data available for United States. But if you were somewhere else in the world, we do have data available for, I believe, like 100 countries in the world. Of course, for each country, we have different data available. So these are all the data categories available for United States, and you can browse it by going into the details, and then there's some interesting data about health care and insurance, how many people have insurance. There's some really interesting data on consumer spending, how much they spend on buying shoes, beer, even domestic beer versus imported beer. I thought that was interesting. And then I can browse by each categories, or I can simply just type the type of information I'm interested in, and these are all the income-related variables that I can add to my existing data. Say if that's what I select, I can go ahead and run this, and then it will attach. Basically, for this income data, the source is U.S. Census data, and then it will acquire that data and then apportioning it to my existing geography. Then I will be able to have income data for my hex bins. Again, I would like to show you, here's the data after geo-enrichment. So I classified the income based on, obviously, the median income, household income, and the red is actually the lower income, and the blue ones are the higher income. Let me zoom in a little closer. So I also configured the pop-up, so I can see for this specific hex bin, I have an income of 42,000, and then compared to the county median income. So it's actually a little bit lower than the county median. And then if I go over here, it's clearly a lot higher than the county median. Okay, so what else could be related to my school performance? Perhaps the crime in the county. So I have crime incidence data. The first thing I did is apply a filter because, Okay. So what I believe is what the type of crime that's most related to the school's performance perhaps is the gang-related crime. So I filtered out my data, gave me the crime incidents that is only gang-related. So that's the type of the crime. So after that, I performed a density analysis, basically the same algorithm as the kernel density in Spatial Analyst that Linda showed. So what I did was I went to analyze patterns and calculate density. And here is my result. So we can identify some areas where we have high crime in LA. So now I had performed aggregation. I performed the hotspot co-spot analysis. I acquired the median household income from using geo-enrichment service. And how do I share this analysis results? And I may want to share the results with the school board, perhaps with the public. So an easy way to share my results is to create a web application. So here, a web application I created, and I want to show you first the web app, and then I show you how easily it is to create this web app. So what I have here is just a simple web app. You can send the URL to anyone, and they can just view it. They don't need to be part of the ArcGIS Online organization. So I have my result from my analysis. Here's the crime density, gang-related crime density. Here's the aggregated hex bins based on my school points. Here's the hotspot co-spot analysis. Here's the median income. And my map is actually all linked. So if I zoom in to this area, which is downtown, pretty much downtown LA, and then I can see these are lower performing schools, and they happen to have high crime incidents. And then this is my income. You can see that they're below average income. Obviously, the aggregation fits the spatial pattern as well. They contain schools that has relatively low API scores. So now I want to show you how did I generate this web app. What I did was here at my web map, I say share, and then I say create a web application. Now there are lots of default templates that I can choose from. And one of them is called comparative analysis, and that's the one I chose. And then I can configure by supplying which web map I would like to include. and then I save it, that's done. That's the web app. That's how I generate it. Of course, if you want to be more customized, and here it even comes with the legend, and you can download the template and modify the code. But without writing any code, I can easily generate a web application. There are different templates available, and excuse me. And one of my favorites is the one with the swipe. So you have something like before and after. You can use that swipe template to do it. Okay. That's my first demo. And switching gear a little bit, the next one I would like to talk about is spatial interpolation. How many of you have used or heard of geostatistical analysis extension? Excellent. Wow. Okay, for those of you who haven't heard about it, it is an extension that contains statistical tools, mostly focused on performing spatial interpolation. As a simple introduction to spatial interpolation is that, say you have sample points with measurements. In California, we have monitoring stations throughout the state that monitors the ozone level. And then it's never possible to monitor everywhere in the state, right? So based on these measurements with existing stations, we can use spatial interpolation to create a continuous surface to have predicted value between the known locations. So where you don't have a monitor station, we can have a prediction based on the existing measurements. So in geostatistical analytic extension, we have some real advanced geostatistical interpolation techniques. One of them is called empirical Bayesian kriging. Without going into too much details, by the way, there are workshops, technical workshops specifically focused on geostat or kriging, but without going into too much details, basically kriging is based on spatial autocorrelation, which is the assumption that if we have spatial features that are close to each other, things that are close will have more similar characteristics than things are further apart. And give you a very simple example. If it's raining on one side of the street, I can easily predict on the other side of the street it's also raining. But I will probably be less confident to say the other side of the town is raining, or I have no confidence at all to say the whole state, somewhere else in the state, is raining. So based on the spatial autocorrelation, so kriging first model the spatial autocorrelation within my data and use that model to create a prediction surface. So let's see a demo. So my demo scenario here is, let me just open up the, this is ArcGIS Pro, by the way. How many of you have seen ArcGIS Pro? Great. So this is part of ArcGIS Desktop. It's a new desktop application. For those of you who are more familiar with the ArcMap user experience, this looks a little different. We have tabs, and to run analysis, you go through this analysis tab. So the points you see here are noise pollutions, the sample measurements that measures noise pollution level in Fort Collins, Colorado, and the noise level is measured in decibels. So what my goal here today is to create a prediction surface so that I can get an idea of anywhere in the city what is the noise level. So as I mentioned, one of the advanced geostatistical interpolation techniques that we have is called empirical Bayesian kriging. And there are some assumptions for when you use kriging method. And one of the assumptions is that my data should be normally distributed. So in order to test if my data is normally distributed or not, I can use the chart function and create a histogram of the decibel value that I have in my data. As you can see, if it's normally distributed, you should see like a bell-shaped curve, and clearly my data is not normally distributed. Well, the good news is empirical Bayesian kriging method allows you to transform your data before you, so it allows you to apply transformation and transform the data to normal distribution before you apply the method. So my input feature here is the one I would like to predict based on. It's my noise sample, and the value is saved in the decibel field, and I can create an output geostatistical layer and output raster. Basically, this stores the prediction value. It's a raster surface that stores the prediction value. And then again, as I mentioned, we can apply transformation. This workshop, we can only go through the overview. I don't have time to go to specific the parameters for these techniques. Again, if you're interested in spatial interpolation, I strongly recommend you to go to the workshop on, there's one on kriging, and there's one on geostatistical analysis extension. So I can go ahead and run this empirical Bayesian kriging, and this is the result. So as you can see that I can get an idea of where the noise level is high in the city and where the noise level is relatively low. And the advantage of kriging technique is that not only it can produce a prediction surface, it can also produce a standard error surface, so that the dark red is the areas we have relatively high standard errors, and the lighter color means we have a value low standard error. As you can see that where we have close to the area where we have a lot of point measurements, and we have relatively low standard error. That makes sense because we have a lot of samples to make prediction with. Okay, so one of the new tools that we made available last year is called EBK regression prediction. EBK stands for empirical Bayesian kriging, and as you can hear from the name, it means this tool combines kriging with regression. So kriging uses existing measurements and based on spatial autocorrelation, and regression allows us to provide additional variables to use in our prediction. So as we know that there are many factors affects the noise level, how close it is to a road, and the closer it is, the noisier is supposed to be. So I have here many explanatory variables. One is the distance to green areas. So the idea is that the closer it is to a green area, the more quiet it's supposed to be. And distance to the interstate, and then road density, and here's the speed. By the way, Linda created this demo, and this one I had to ask her what it means. So she combined the railroad speed with the regular road speed. So the idea is the higher the speed of the traffic, the more noisier it's supposed to be. So now let's go ahead and run this EBK regression prediction. So again, our input is the noise samples, and our dependent variables is the one we're trying to predict is saved in the decibel field. And now this is the new part. This is where we can provide additional explanatory variables, which are in our which are layers that I showed earlier: the distance to road, the road density, the distance to the housing density, distance to industrial areas, and so on. And I can go ahead and run this analysis, which takes a few minutes. And I also want to show you what I had created. So here's the result from the EBK regression prediction. Let's compare the one from EBK. Let's put them side by side. So as you can see, left and right, this one to this side, that's the result from the empirical Bayesian kriging. The one to the left is from EBK regression prediction. As you can see that just because we provided additional factors that influencers that affects the noise level, we actually can get a more detailed results, which is the advantage of EBK regression prediction is the prediction result will be more accurate than using either kriging or regression alone. Okay, how am I doing with time?
Not bad.
Okay, good. Okay, so let me know if you have any questions. I know that I jump this. These are very different type of analysis. I jump pretty a lot. And if you have any questions, just let me know. So our next analysis will be suitability analysis. And that is one of the most popular analysis that people use spatial analysis extension for. So our demo scenario here is I would like to find the best place to build a wind farm in the North Sea area. And because of its natural conditions, North Sea is one of the areas in the world has most wind turbines built. So when we consider to find the optimum place to locate something, the first step is always to identify the criteria that is important for the suitability. So what are the most important criteria? What do we need in order to build a wind farm? Obviously, we need adequate wind power, wind speed, and we need to have enough wave power. And because the cost, to lower the cost, we want to have the wind farm relatively close to the existing ports, and we want to avoid ship traffic, and we also, for cost reasons, we want to build it in relatively shallow water. And then we want to avoid the marine protected area. So these are our criteria, and then we can generate surface for each of our criteria. So then naturally we have all the criteria, and we want to combine them and to find what is the most suitable place. But the measurements for each of these criteria will be very different. The wave power is measured in 1 unit, and the distance to seaport probably by kilometers, and the water bathymetry probably in meters, and we can't really compare these. They're in a different scale, different unit. So we have to go through a reclassification step that scale them, reclassify and rescale them into one scale. So what I do here in using Spatial Analyst fuzzy logic tool that turns each of my criteria into 0 to 1 scale. And fuzzy membership tool, basically, it's a probability, calculating the probability. 0 means you're not suitable at all, not a member at all, and 1 means a perfect number. So most likely it's somewhere in between, right? So if you have a very high wave power for that specific criteria, it's probably closer to 1, and then very low will be closer to 0. So after I reclassify them, then I can add them up. So what they call it a raster overlay, and then I calculate the best sites that is most suitable for my purposes. So let's take a look. Again, this one I use ArcGIS Pro. So let me open my. So here I have my study area is the North Sea area. I have the North Sea buoys. I have a buoys location that each buoy location has an attribute that with the measurement of wind speed as well as wave power. And I have ships. And then these are ship locations which I can use to generate a density surface. Okay, so Linda mentioned earlier, let me see how I can best. Linda mentioned earlier that in analysis, we can actually create models using Model Builder to automate this process. So what I also like to show a model because it's a great way to document my analysis workflow and steps. So here, from the left, these are my input data. So from the port, remember distance to the port is one of my criteria. So I use Euclidean distance. That's one of the method in Spatial Analyst. I use that to generate a cost distance surface. And then from the buoy points, I use EBK, empirical Bayesian kriging, to create a continuous surface so that anywhere in the North Sea area, which is my study area, I get a value of predicted wind speed and wave power. Okay, so here, empirical Bayesian kriging is just part of my step for my analysis to get the data ready for my analysis. So same for ship events, the locations of ships, and I use kernel density and create a density surface for the depths of the ocean. I actually already have it in raster surface, which is bathymetry data. After that, I use the fuzzy membership. That's the reclassification rescale part. And after that, we do a fuzzy overlay. And one last step, because I have also existing marine protected area, I have to subtract that area from my suitable surface. So if I go ahead and run this model, lots of steps in there. Any questions at this point? Okay. I don't know what is going on there. So while it's validating, normally it shouldn't take that long. Oh, okay. I want to show you, here's what I have. So see the wind speed after empirical Bayesian. This is the surface it creates. And this is the wave power. So these are predicted surface created from empirical Bayesian kriging. And this is my shipping density, and the distance to port, and so on. Let's see if our model is ready to run. So now I validate the model, and I just go ahead and run this. And so basically it prepares my data for analysis and rescale it to 0 to 1 scale, and then do an overlay, fuzzy overlay, and then subtract the protected area. I should then get my output. Yes.
So I understand you did the creating to create the surfaces.
Yeah.
Then what was the tool that you're like giving? You decide, okay, these are the wind speeds that equal to 0, and these are the wind speeds that equal to 1. What tool is that?
That's called fuzzy membership.
Oh, that's the fuzzy membership.
Right. Yes.
Can you tell us a little bit more about the fuzzy membership algorithm behind that reclassification method? Like, how do you reclassify a value from 0 to 1? What is the algorithm behind that?
You actually have to provide that when you use the fuzzy membership tool, you have to say what is your high value based on your measurement, say in wind speed. What's the high value you consider most from this value to this value is most suitable, from this value is least suitable. And then the tool automatically rescale it. And I think if you want to know the real detail algorithm, there are spatial analyst, specific spatial analyst workshops you can go to. And then I can also help you afterwards. I can explain to you. So this is the output from my overlay of all the criteria combined. So the darker the color, the more suitable it is for my wind farm location. Okay, so we have 2 more demos. So, okay, yeah. We see like how we can perform suitability modeling, and this is a raster analysis based on tools we have available in Spatial Analyst. When there's traveling involved on a transportation network, we have other algorithms we can use to choose the best place to put a new facility. So that is like network location allocation algorithm we use there. And the goal is always, number one, to minimize the cost, and the cost is travel cost. So travel cost can be travel time or travel distance. And then another goal is always to maximize the demand we serve. So a hospital, for example, can have serve a specific, have a capacity, serve a certain amount of population. Say we're building a new neighborhood park. We want to maximize the number of people who can use the park within certain amount of walking distance. Now, walking distance would be the travel cost. We want to minimize that cost and maximize the demand we serve. So here's the demo scenario. So this is a county in North Carolina area. I happen to have data for that county, and then I have 8 existing health clinics. In the winter time or fall time, flu season, I want to add additional mobile clinics so that I can give my county population flu shots. And in the past, the county chooses existing library locations as the mobile clinic locations just because it's easier for people to go to, easier for them to find. And the budget I have this year allows me only to build 4 new clinics. Okay, let's see how it works. You can do this in Network Analyst extension using ArcMap. And what I want to show here is the in ArcGIS Online. This one's also implemented. It's one of our latest tools from last year. So here I have my county boundary. I have existing 8 health clinics, and here are my existing library locations. Obviously, I have more than 4 libraries, but I only have budget for 4 new locations. So what I do is I go to analysis and use the choose best facilities. And there are many, you have to first identify the goals. And in my specific scenario, my goal is to maximize the coverage of my clinics. So how do I measure my travel cost? I'm going to measure it based on drive time. I'm not going to choose traffic, just use the average traffic. And the travel direction, the demand here is the population that living in the county. So in my scenario, the population will drive to the mobile clinic or clinic. So the travel direction is from demand to facility. And my demand location, again, demand is the population. So here I'm going to use the census block groups points in the county. And the count, the amount of demand comes from this field called population. So I know from each block group how many people live in that group. The travel cost measurements is going to be a constant 10 minutes, meaning I do not want anyone who drives more than 10 minutes to a clinic. Okay? And then I can go ahead and what are my required facility? That these are my existing clinics. They already serve the population. And my candidates will come from the libraries. And again, remember we have budget only for 4. So I specify 4 here. So I can go ahead and run this analysis. And here's the result I would like to show you. So these are the points. The diamond shapes are my existing public clinics, and the square shapes are libraries, and the red ones are the ones that were not chosen, and the 4 green ones are the ones that been chosen based on the location allocation algorithm, the one that would maximize the coverage for my clinics. So I'll show you, if I draw these lines, these are the lines travel from the population, so you can get an idea from which block group people travel to which clinic. Okay?
Should probably wrap up.
All right. I have 2 more minutes left. I think, well, this one I'm going to show real quick. So we showed you how to run analysis in ArcMap. Linda showed it. I use ArcGIS Pro, ArcGIS Online, and sometimes you can just create a web app and you publish your geoprocessing service in your from ArcGIS server, and you can just consume that in the web app. So in this web app here, it does not look anything at all like a GIS software. So what this does is I just randomly select any area in the US, and it summarized the land use type within the polygon I delineate and gave me a summary report. And the user of this web app doesn't even need to know what GIS is. They just need to know this is a tool I use to get my land use summary. So the idea here is that you as a GIS analyst can publish, can be the expert, create models, run analysis, but to share your analysis with your audience, they may not even need to know what's going on. Okay. Takeaway points. Spatial analysis brings the true power of GIS. We work for the analysis team, so we are more or less biased on this point, but we believe that is really the strength of GIS, and by analyzing the spatial data, by understanding how it's related to other spatial data, you can really gain insights and gain useful knowledge and make good decisions. And we do provide advanced analysis techniques through different applications we have. And also, meanwhile, by making it available online, by making it available in a web application, we want to lower the entrance bar for using analysis. So, there's many sessions about analysis throughout the users conference, and our workshop basically gave you an overview. We covered a lot of different type of analysis, but unfortunately we didn't have time to go in detail in any one of them. But please, you're welcome to check out all the other workshops which have more specific focus. Last, which is not the least important for sure, is we would like to have your feedback with our workshop, what you like, what you don't like, how we can improve on this. Thank you very much.
Thank you.